We have Professor Stefano Morra from University of Paris 8, and today he will continue his lectures on complete cohomology for Shimura curves. Professor Morra.
Thank you. So thank you very much again, and thank you very much for being here. So once again, this is the bibliography. And I wanted to start the course today with some replies to the question that I got yesterday. So first of all, it's a reply to the question of Eknat about the relation with the Borel-Serre compactification. So yesterday I was talking about the paper of Asher concerning the fact that the arithmetic quotient, they always have a compact subspace, which is a deformation retract. And the question of Eknat was, what is the relation with this Borel-Serre compactification? So the point is that actually the relation is not so easy. And this was the subject of a Duke paper in the 1997 of Ash McCannell, which is called Cohomology at Infinity and Well-Rounded Retract for General Linear Groups. So what is, very briefly, so what is the point? The point is that here you have your symmetric space for GR. You have the Borel-Serre compactification, and this is the subspace, the subspace which will give rise to the compact deformation retract. All these maps are gamma equivariant. Gamma is the congruent subgroup. So this space is the space of so-called well-rounded elements. So they are lattice such that the set of minimal length element span R to the n. N is the dimension, it's the GLN, then not the JLN. So the theorem of Ash and McConnell, is that so if one considers the deformation retract from X to the space of well-rounded element, you can extend it to the Borel-Serre compactification to a gamma equivariant map. So this is proposition 7.6 in the Duke paper. And the difficult point is to show that this extension is actually a homotopy equivalence. So it's still a retraction. So this is difficult, and this is shown in proposition 8.3. And the reminder of this paper, this comparison paper, is that is to compute the cohomology of the boundary. So you can extend, in summary, the deformation retract of Asher extend to deformation retract on the Borel-Serre compactification. So in particular, the cohomology of the Borel-Serre compactification is computed by the cohomology of this particular compact of so-called well-rounded element. And there is a spectral, there is like a commutative diagram which lets you compute the cohomology of the Borel-Serre compactification and also to describe in some different way the boundary of the Borel-Serre compactification via this deformation retract. Okay, so this was the answer, partial answer to the question of Eknat. Then there was another question about the unitary action. So this is very important, and it was a very good question because I was a little bit sloppy in the definition of the complete cohomology. By the way, can you read it properly? Hope so. Don't hesitate if it's not. Yes. So what is the, thank you. So what is the point? The point is that I remember that I was defining the completed cohomology. Sorry, this is not very readable. It was the limit over S, and then the in that limit of this guy, right? Sorry, Hopla. It was the in that limit of this guy. So these Kp are compact such that W0 is stable under Kp. So this set is cofinal in the set of all compact. So you remember that when I was defining the space H tilde, I was not taking care of this fact, the fact that we should choose carefully the compact open. And it's okay because this set is cofinal, so the space do not change. But if you want to understand the action of the group, then you have to be very careful. Because, you see, the proper definition in order to understand the GQP action is this. You have to take you have to tensor over E, and then you have to take the direct limit over all lattices. The point is that this stabilizes this direct limit. It eventually it stabilizes, but you have to take the limit over all lattices. And why is this important? Because the GQP action on the space, on this space, the GQP action, when you put rational coefficient, is given as follows. You are changing the lattice, you see? When you multiply by G, you change the lattice. And so this action is isometric, so it's a unitary action at the end of the day, if the representation is the trivial representation. Is the trivial algebraic representation, because the lattice then is exactly the same. But otherwise, as I mentioned to you, the action is not unitary. And this is discussed in the Hamilton 1 before lemma 2.2.10. Okay, the third question that I wanted to reply to is the question of Hida. So his question was the following. I just remind you. And then we start from here. So once again, this question is actually answered in the paper of Koolhaase, the Cohomology of Locally Analytic Representation, which was published the early 2000 in Krelle. So the question of Hida was the following. We have the functor of locally analytic vector from Banach space representation admissible to locally analytic representation, which is exact. And Hida was asking, well, in order to compare the higher derived functor, why cannot we use the Grothendieck spectral sequence, right? Because we know that the functor is exact, so the J contribution is 0. Well, what is the problem? Well, the problem is very easy, unfortunately. That this category is not abelian and doesn't have enough injective. It's not abelian, sorry, it's not abelian. And even if I take the full abelian subcategory, well, this full abelian subcategory still doesn't have enough injective. So one cannot even ask for a Grothendieck spectral sequence. All right. So now it was a very good point to start because now I can take back from where I left last time. So recall, so where we ended yesterday. Sorry. We recall where we ended yesterday. So we wanted to understand the following theorem, this comparison theorem. So theorem that the HI stable of a V is isomorphic to the Lie algebra cohomology of what? Of the locally analytic vectors. So V, I remind you, V is an admissible Banach space representation of, say, GZP of E with a continuous action of G, with continuous GQP action. All right, so in the proof, we already showed, so we showed that the H0 stable of V is equal to the H0 of G, V locally analytic which was the motivation of the question of Hida about why cannot we use the Grothendieck spectral sequence? Once again, because the category, unfortunately, is not a Boolean category of locally analytic representation. Okay, so now we want a case I strictly bigger than 0, and the upshot is that we have a resolution So we have a resolution of V analytic, which was looking as follows: 0, V analytic, and then we had the space of analytic functions over GZP, E, and here we have a certain direct sum, I don't know, R1, and then, and so on. And here we have an action of the universal enveloping algebra of G. This is because the Lie algebra of GCP is the same as the Lie algebra of GQP. All right, so let's say this is our complex, which I called C analytic V naught. This is our complex. And so the complex C analytic V naught computes the Lie algebra cohomology. It computes the Hij V locally analytic, provided that this complex is acyclic. If the complex C analytic V naught is H naught G acyclic. So now the goal is to show that is just to show that the Lie algebra cohomology of the space of analytic function is 0. So show that the Hi of G, here we have C analytic GZPE, this is equal to 0 for all I strictly bigger than 0. Okay, so this is what we're going to do in the next few minutes. So in order to answer this question, we need some classical tools from homological algebra. And so we are going to introduce the Chevalley-Eilenberg complex. Eilenberg complex. Once again, a reference for all these is the book of Weber, for instance. And this is paragraph 7.7. So if I take a module over the universal enveloping algebra, so if M is a module over the universal enveloping algebra of a Lie algebra over a field, then the Lie algebra cohomology is computed as follows. So is computed by the following complex. So we take the Hom space as QP vector space of the wedge product of G. Here we have M. So the boundary maps are very explicit in terms of cochains. Here we have wedged I+1 G, M, and so on. So we have this complex, which I called C M bullet. All right, so what is the key point? Well, the key point is that now we want to specialize this to local analytic function. So we specialize to M, which is given by the space of locally analytic functions over, so for short, forgive me, for short, let me write H. So H now by definition is going to be GZP, is our p-adic compact analytic group, HE. And so what is the key point in all this? The key point is that the space of local analytic function can be reinterpreted as the global section of the structure sheaf over the local analytic variety H. So this is, sorry, this is the structure sheaf of the locally analytic variety H. And so what is the upshot of this? The upshot is that actually these are global sections of the differential Y. So let's see just a little bit more in detail. So here we have the home QP of the wedge product gamma M. Well, for us now, so this is this is equal to the wedge product IG. I take the dual, I tensor over QP over the global section. And this, so the key point is what? The key point is that this is isomorphic to the global section of the sheaf of differential, of locally analytic differential, because this we are considering the local analytic functions. So here I take omega I H QP. And this is why? This is because the tangent bundle is trivial, because the topology is totally disconnected. So that since wedge G times QP gamma H O, this is equal to the wedged I of the global section of the tangent bundle. Tangent bundle. And note that the tangent bundle is trivial. It's just G times H, because the topology is totally disconnected. As H is totally disconnected. So this is a good news, because we can consider the RAM complex now. So this is literally the global section of the RAM complex. So the upshot is that the sheaf, the complex, which I called CM, so CM naught, is, let's say, are the global section of the RAM complex. So here we have omega I H over QP, omega I plus 1 H over QP, and so on. So this is C the RAM of H. And now the RAM complex, so these are once again the local analytic differential. So what is the key point now? The key point is that H is a smooth variety over QP. So the key is that H is locally isomorphic to a bunch of copies of ZP to the dimension of H. And so H is smooth. H is smooth. And so this means that by Poincaré lemma, it means that the theorem complex is a resolution for the constant sheaf. So this means that, so by Poincaré, means exactly that C theorem of GZP is a resolution of the locally constant sheaf over H. So now, what is the key point? The key point is that, again, the topology on H is totally discontinuous. So H is totally discontinuous. And so what does it mean? Well, it means that if I take the global section, I still get a resolution of the constant sheaf. So this means that the global section of the theorem complex of GZP are a resolution of the global section of the constant sheaf, are a resolution of the global section of the constant sheaf. And so the upshot is that the theorem cohomology is 0. So the HI theorem of GZP is 0. But this is exactly what we wanted, because this, by what I said before, this is exactly the HI of GC analytic GZPE. And so this ends the proof. So once again, I just want to remind you, so now we know that HI stable is the Lie algebra cohomology of the locally analytic vectors. Recall that we want to show that certain derived factor of the HI stable are 0, computed when the V is the H tilde 0. So let's see. So what are we left to prove now? I just want to remind you that we are left to prove the following. We are left to prove that the HI of the Lie algebra cohomology, so for us, remember that this is GL2OFP restricted to ZP, computed against the H naught tilde of K upper P W locally analytic. We want to show that this is 0 for E equal 1 or 2. So some comments. So first of all, we note that, so let me take another color. So first of all, we know that this guy is isomorphic to the H tilde 0. So remember that the action over here is polynomial because it's an algebraic representation. So I can pull out the W. So this is, I can simplify a very little bit as follows. I take the locally analytic vector of this representation, which is tensor up over E by W. And this is since as W is algebraic. And what is the idea in order to prove this equality? We have to break it up according to a decomposition for the GL2. So the idea is the following. First of all, we want to decompose the Lie algebra. So we want to decompose, so GQP, I can write as GQP dev, so G, the derived subgroup, times the center, ZGQP. So what is the point? The point is that this is easy, since this is a semi-simple group. There are some classical results in the algebra cohomology which let us kill part of this. And here we have to study the action on the connected component. Study the action on the connected component of the modular variety, YKC. So this is the first step. And the second step is to use Cunet formula. We are going now to put in force this strategy. All right. We are now very close to the achievement of the main theorem. Okay, so let's consider the first point, which is the most difficult. We have the decomposition of the Lie algebra. So GL2 is SL2 times Z. Z is the Lie of the center of G. All right, let's write chi to be the central character of our algebraic representation. So this is the central character of W. So let's take back the decomposition that I wrote just before. We have that H naught K upper P E tensor over E W. These are the local analytic, log N. I can split it up in such a way that we have some trivial action of part of this Lie algebra. So it means the following. It means that here I can consider H theta not K upper P E locally analytic tensor chi tensor chi minus 1 tensor W. So what is the advantage of this writing? The advantage is the following. So advantage. Here, SL2, the Lie algebra of SL2, acts trivially. So we will see why in a second. So here, SL2 acts trivially. Here, the center acts trivially. Z acts trivially. Here, the center acts non-trivially. Z acts non-trivially. And here, SL2 acts non-trivially. Acts non-trivially. So what is the key point now? The key point is that we can easily deal with these by classical lemmas, namely the Whitehead lemma. So I will write here in red. Let's take care first of this object. So the Whitehead lemma is a classical lemma, which you can find the Dibel. So is in Vibel 7.8, tells you that the HI, the Lie algebra cohomology, the HI SL2 of this guy is 0 for I strictly bigger than 0. And why? Since this is a semi-simple Lie algebra. Since SL2 is a semi-simple Lie algebra. And of course, this is a finite dimensional vector space. The dimension of chi-1 times W is finite. Okay, so we keep this part. Now we have to deal with this part, which is less immediate. So we need, in order to deal with this part, we need the following lemma. Well, so the first point is that the SL2 acts trivially on here. I was mentioning, I was claiming this. So let's see why. So SL2 acts trivially over the H naught tilde of K upper PE locally analytic tensor chi. And moreover, we have what we want, meaning that the HI of the algebra of the center computed over H tilde naught K upper PE is 0 for I strictly bigger than 0. All right, so let's have a look at the proof. Remember that we have our Galois cover. So we have Y of K upper P, and here I consider GL to ZP of C. So if I consider the principal congruence subgroup, where we have the following Galois cover, here I consider KPN. So this is the principal congruence subgroup of level n. So the matrix which are trivial mod P to the n. So this is a Galois cover. And this induces a torsor at the level of the connected component. So here we have the pi naught of Y K upper P K lower P of C. Here I have the connected component of Y K upper P K lower P principal level N. So this is a O FP cross mod. Here I have sorry, P to the N. Oh no, sorry. Can you read it? It's readable. Sorry for this. Up. So this is pi to the n. And here I take the units. So this is a torsor over here. So what is the key point? The key point is that this is isomorphic to the. So here we have a GZP action coming from the GZP action here. And the key point is that this is isomorphic via the reduced norm this is isomorphic to, we take the torus of the finite adelic point, T, Q, and here we have the image via the norm up of the K upper P, K lower P. And the action here factors through here we have a O star FP. And this happens via the determinant. So in order to see this, so this is in Caraiol, which is based on Deligne. So this is Caraiol paragraph 1.2, which is based on Deligne theorem 2.5. I just want to recall you that Deligne, this reference is the Bourbaki talk of Deligne about the work of Shimura. And this is the compositio paper of Caraiol on the bed reduction of Shimura curves. All right, so we see that ST2 acts trivially over here. And why is this important? Well, we are almost there, because we can conclude the following. So hence we have that the H naught of K upper P, K lower P, level N, with O pi S coefficient. So this is isomorphic to, by what I have just said now, is isomorphic to the space of functions over O F. So this is OFP mod pi to the S. Ah, no, sorry. Pi to the N star with coefficient in O mod pi to the S. And this is a direct sum over the connected components of pi naught, the connected component of the base, so K upper P, K lower P of C. And so now we pass to the limit. So now we take, the lim over all level at P and over all S. We conclude that the H tilde naught of K upper PE is isomorphic to what we wanted, meaning that it's isomorphic to the space of continuous functions of OFP cross E. Direct sum the number of connected component. So direct sum the number of connected component of the curve. And now we are in business. Why? Because we know that if I take the local analytic vector, so if I take the local analytic vectors here, I obtain the space of local analytic functions, and we know that the Lie algebra cohomology is 0. So as before, as for the comparison theorem, sorry, for the comparison as for the comparison theorem, we conclude that the HI of the Lie algebra acting on this H naught tilde K upper P E locally analytic is 0 for all I strictly bigger than 0. And since this space is isomorphic, so this space is insensitive to the twist by a character. So since C continuous of OF cross is isomorphic to C continuous OF cross P E times chi as OFP rep, we get what we wanted. So we get that HI. These are infinite, of course, they are infinite dimensional. So these are isomorphic. So here we have HI Z H tilde 0 K upper P E times chi is 0 for all I strictly smaller than 0. Okay, and so now we are happy. Now we are happy because we can conclude by the Cohomology formula. So point number 2. Sorry, maybe I can change page. So point number 2. We use Cohomology. Well, this is a standard result. For instance, you can have a look in the Borel-Wallach book on continuous cohomology to get like a clean reference to this. We have that the HI of a product, so the Lie algebra cohomology of G1, G2 of V1 times V2, this is isomorphic to the direct sum of, and then now we can take tensor product of the individual pieces. So this is the direct sum over the integer a plus b equal I of H A G1 V1 HB G2 V2. This is over E. And hence, what happens, for instance, let's give very explicitly, for instance, if I take the H1 of G2 of my H tilde naught KPE analytic tensor V. So this is going to be isomorphic to the following. We have, first of all, we have H1 Z H0 K upper PE analytic times chi, and this is tensored up with the H0 of SL2 chi minus 1 times W. Direct sum H0 Z H0 tilde K E analytic times chi, tensored up with the H1 of SA2 chi minus 1 times W. And now we have seen that this is 0 by the previous lemma, and this is 0 by the Whitehead lemma. And so we conclude that this is also 0. And so we conclude by the Cohomology formula and the previous vanishing of the various Lie algebra cohomology for SL2 and for Z. So we conclude that HI of the GL2 H tilde naught K upper PW analytic, this is 0, and this ends the proof. So the conclusion, I just want to recall you the conclusion. What is the conclusion? We remember that we have this map, so we have H1 of K upper PW. So this has dense image in the H hat 1 of KP. So this is dense W. Remember that in our specific case, the H1 hat is the H tilde, sorry, the H tilde 1, because the Tate module doesn't have torsion in low degree, and because our curve is compact. And this map factors via an isomorphism through the smooth vectors. So H1, Kp, W, smooth. So this is the main theorem that I want to discuss about in the first part of my course. All right. So now I can switch to the second part, which is the.
May I ask a question? What do you do for H2 in the Kuhnert formula? Do you have a Poincaré duality here?
We do have a Poincaré duality, yes. We do have a Poincaré duality because now we have a curve, and the curve is compact, so the H0 is dual to the H2.
Okay.
In fact, I mean, I just permit, because this question is actually related to, I'm looking for my notes. I'm looking for my notes. So the point is that, so just to mention, this is the lecture of yesterday. This map, this isomorphism, comes from an edge map here. At the very beginning of the edge map is I was just putting somewhere because I wrote it down. Is here we have the beginning of the edge map. Mm-hmm. And so we just proved that the H2 stable is 0. Mm-hmm. Because we proved that H2 stable is exactly the H2 of Lie with the local analytic part.
Yeah.
So it's even not necessary to consider the Poincaré duality, even though it's absolutely fine. One can also invoke the Poincaré duality. Okay. But once again, Poincaré duality in this case is very specific to the fact that we are working with a curve, with a compact curve. Okay, so now I would like to discuss the further structure that we have on the completed cohomology, because I would like at the end to mention a result of flatness of the completed cohomology for Shimura curve over a local deformation ring. So now we have, say, section 4. Ecke actions and relation with Galois representation. So first of all, we would like to first of all understand the Ecke action. So the point is the following: the motivation is that if we change the time level, then we can reconstruct the space of automorphic form. So recall that by Franke's theorem, if we consider, so this is the classical cohomology, Hi, so here I consider Yk with complex coefficient in the local system Pw. I take the limit over all finite adelic points. Well, this is isomorphic to the G infinity K infinity cohomology. So this is the Hi of what? Of Lie. Let me call this. So I write every in detail now. So Lie GD, the real point, and here I take the Lie of K infinity. So this is the maximum compact of the real point of G. Here I take what? I take W tensor the space of automorphic forms over G, GQP. And here I take the adelic point. And well, I have to take care of the infinitesimal character. So here I take some invariant, so the torsion part, and I have to take again here here I have R times the connected component equal to Z, zeta. So these are data. So these are data from the central character of the coefficients. And this GD is the kernel. So this is the kernel of the following group. So the following map. So we have G goes to the center of G. So the restriction of scalars of the GM. And here I consider the maximal split torus quotient, which is just GM. So this result is Franke. It tells us that this cohomology, this cohomology actually encodes part of the automorphic classical automorphic representation. So now, so this is Franke. So now the key point is that I can repeat all the previous construction to obtain a completed cohomology with arbitrary levels. So I can put an automorphic action. So if I consider now a tame level, Kp prime, inside Kp compact open, I again have a Galois cover. I again have a Galois cover. Here I have Kp upper, Kp lower of C. So this is Galois. And here I have K upper P, K lower P, C. A Galois cover. And we can obtain the following commutative diagram of exact sequence. So we, as before, we can obtain the following commutative diagram of exact sequence. So here we have the Hi hat of K upper P W, H tilde I K upper P W. Here we have the Tate module, H I plus 1, K upper P W. And here we have injected maps into the smaller level situation. K upper P prime W, H tilde I, K upper P prime W. And here I have VP, H I plus 1, K upper P prime W 0. And the key point, so here we have an action. Here we have an action of K upper P, K upper P prime. Oh, sorry, upper P prime. And the key point is that we can reconstruct them. So these are closed embedding. Actually, this is the zero map. I mean, these are zero. So these are closed embedding. And moreover, they let us identify the subspace as the space of invariance. So we can identify the space Hi KPW can be reconstructed as the space of Kp invariance over Kp prime invariance of Kp prime W. So the proof is essentially is formal, but the only important point in the proof is that it's one of those situations we have to be very careful about the change of lattice. So just one word about the proof. So remark on the proof is that we are using the following fact. We are using that if H is a finite group and V is a vector Hausdorff vector space over E, with a continuous action of H, then the map, the averaging V to the H, 1 over the order of H, sum H times V, is a continuous projection. So we want to apply this lemma to the following situation. We have to be very careful because now we have integral structures. So here we have Hi Kp prime W naught. Here, first of all, I have to multiply by 1 over H, which now is the quotient group K upper P mod K upper P prime. So here I have Hi K upper P prime. Sorry. Upper P prime 1 over H times W naught. So this is the multiplication by 1 over H. And here I have the trace map, which comes from the fact that I have a Galois cover. So here I have Hi Kp. And here I have 1 over H W naught. And then here I have the Hi Kp prime W. So this is tensoring over E. Here I have Hi K upper P prime, pardon, sorry, upper P W. And here I have the map, which I was calling pi H. And here I have the inclusion. And so this is the identity. And so what is the key point? The key point is that when I do the completed cohomology, well, these spaces are insensitive to the choice of lattice. And so the key, so this I call this map H pi H, I don't know, not. So the key point is that pi H extends to a continuous projection from the Hi Kp prime W naught tens E to H theta I Kp 1 over H W naught times E. But the point is that eventually, when I take the limit over all possible lattices, well, this destabilizes. And so this is a continuous projection which satisfies the condition of the lemma. So my point, the point is that you see that here you have to be very careful because you are changing the lattice in order to apply classical results here. But the upshot of all this is the following. So the upshot is that the upshot is that we can define the space of completed cohomology H tilde I of W to be the direct limit over all K upper P of the H tilde I of K upper P W, and the theorem, this is in Hamilton 1, is a theorem 2.2.16, is that we have an action, so we have an action of the finite adherse over the completed cohomology. So we have a Banach space action of GQP and a smooth action of G finite upside P. So this is smooth. And this is admissible Banach. And we can reconstruct the space at finite level by taking invariants. So we have H tilde IW. If I take the invariant vectors, so this is isomorphic to H tilde I K upper PW. And the key point is that the space of locally algebraic vectors H1 tilde E locally algebraic is actually given by the image of the H1W tensor W check over algebraic, irreducible algebraic representation, irreducible algebraic rep of G over QP. All right, so I think I finished my time for today. So the goal of tomorrow, so goal, we want to endow this H tilde 1 of K upper P O with, well, first of all, we want to understand the Heare action. Whoops, sorry, the Heare action. Then we would like to localize at a suitable maximal idea in the Heare action related to a Galois representation. And then we would like to show that this guy receives, sorry, this guy receives an action of a local Galois deformation ring. And the action is faithful. And we will see that the faithfulness of the action crucially relies on the lecture of Benjamin, where he considered a result coming from a dimension theory as a modulus over the Mazur algebra. All right. So I will stop here for today.
Okay. Thank you, Professor Morra, for this nice presentation.
Thank you.
Are there questions for the speaker?
Whoops. Oh.
Any question? Okay. Okay. So if there are no further questions, let's thank the speaker again.
Thank you. Thank you, everybody. Thank you.
Thank you, Professor Morra. And with this, we conclude the morning session. The afternoon session will be resumed approximately in 55 minutes. Thank you all.